Let's discuss about telescope design and optics. Today, I think it will be a little bit longer video because we have to discuss a lot of things like exit people, entrance people, and few concepts here. So we have to understand the base of the optics to understand actually optics of telescope and design how it makes, and it makes sense then. So that's why I make video of telescope after later, around after 14 15th video. So we have to understand the basics that we have discussed already to understand a comprehensive understanding of the telescope. So let's move. So basically, telescope is an instrument that magnify the apparent size of the distant object. Basically, telescope for the distant object and magnify the apparent size of the distant object. Generally focused for infinity, but can be made for near vision. Can be made for near vision, and sometimes for near vision we call it telemicroscope. Not microscope, but but not microscope, but generally we call it. I'm sorry. Generally we call it telescope, but if telescope near used for near vision or intermediate vision, it will call telemicroscope. Okay, so telescope for optics, there are two elements that central important: objective lens and eyepiece or ocular lens. Since this ocular lens or eyepiece it's towards our eye, that's why it's called eyepiece. And since this lens, objective lens, is towards the object which we are trying to focus or trying to view, it's called objective lens. Okay, the nominate. So again, we call telescope because tele is distance and scope is to view. Okay, so we have to understand the how it is nomenclatures. So in case of objective lens is always plus lens, isn't it? So ocular lens is plus lens or minus lens. Plus lens in case of Keplerian telescope, minus lens in case of Galilean telescope. Okay. So optical principle, a focal telescope means there is no focus. That means, see, parallel light come to the objective lens and parallel light emitted from eyepiece. That's why it's called afocal, not focusing. Okay, a focal telescope. See, why it is afocal? It's central important. Afocal, there is only one condition telescope becomes afocal is the separation between objective and ocular lens by their absolute value of focal length. It means, okay, I'll tell you in the pictures, but it's absolute condition. We have to meet this condition to make a focal telescope, that the separation between objective and ocular lens by their absolute value of focal length, and it produce only angular magnification. Okay, there is no relative distance magnification, only produce angular magnification. As we have discussed in the previous video, the angular magnification means magnification image angle subtended by image and angle subtended by object. Simple. Okay, parallel rays light incident from infinity and emerges parallel. So there is parallel light come from infinity and parallel light emitted from eyepiece. So there is equivalent power of telescope is always zero. Okay, don't confuse with it. So magnification of telescope is depend upon minus d objective eyepiece divided by uh, objective lens power. For focal telescope, when we make telescope from afocal to focal, so focal telescope, which is sometimes called telemicroscope, made for intermediate distance or near distance, and made due to relative distance magnification. Focal made due to referred telemicroscope sometimes. Okay, I move forward. So optical principle of microscope, and I'm not talking about microscope definitely. So let's skip it. Think we have to skip. So type of telescope is Galilean telescope and Keplerian telescope. We sometimes simply Keplerian telescope for the far distance, like to see moon and something. In Galilean telescope, we think that it's used in more useful in case of low vision, because Galilean telescope creates the erect image and Keplerian telescope creates an inverted image. Okay, we will discuss in optics basically. So Galilean telescope primary focal point of ocular lens is coincide with the secondary focal point of object lens. It's always not. It's not just for Galilean telescope. It's always for all telescopes, whether it's Galilean or Keplerian. It's central and important to understand. See, primary focal length of ocular lens. Ocular lens, primary focal length. Secondary focal length of objective lens is central. If it is objective lens, its secondary focal objective lens is always positive, always, no matter what. Its focal length, secondary focal point is here, and it's here. We know another length, no matter what it could be. It could be plus or minus. If it is plus, then it's primary focal point. The secondary focal point of objective lens and primary focal point of eyepiece. It should coincide. It should coincide, and that's the principle of no matter what. It's Galilean telescope or Kepler telescope. Okay. So in case of Galilean telescope, the ocular eyepiece is ocular lens is always negative. In case of Kepler telescope, ocular eyepiece is positive. So it makes erect image. That's why a magnification is positive. It makes because upright image and virtual image. Okay, we know it, isn't it? We have talked in case of magnification. If magnification is plus, it means object is erect, image also erect. So simple. So this is the picture of Galilean telescope. See, in case of minus lens, I have already discussed this concept. Let's in case of minus lens, if you want its secondary focal point, it lies here, isn't it? It's like opposite. In primary focal point here, isn't it? In case of plus lens, primary focal point is here, secondary focal point is here. Like f is here and f dash is here. In case of this, f is here, f dash is here. Image space and objective space on all these things. See this picture, objective lens, this is the objective lens, has focal point here, isn't it? Isn't it focal point? So secondary focal point of objective lens coincide with primary focal point of eyepiece. Eyepiece in negative lens, primary focal point is here, so coincides with primary focal point of eyepiece. And then parallel light comes, exit parallel light. So there is no focus here. So that's why afocal, isn't it? Parallel light comes and parallel light goes. But angle sustained to, so this is the angle sustained by object, and let me tell you one thing, and this is the angle sustained by image. So angle sustained by object is far lesser than angle sustained by image, and then this divided by this, isn't it the magnification, angular magnification? So that's how it plays. Why it's central important, why it functions like that, because it functions in only in angular magnification. So you have to understand the angular magnification first. So let me tell you again, the angle sustained by eyepiece, that's actually image. Angle sustained by image is larger than angle sustained by object. The angle sustained by image divided by angle sustained by object is angular magnification. And that's how it creates magnification. And even though we know that the Galilean telescope or Kepler telescope, equivalent power is always null, zero, always null, zero. Okay. So Kepler telescope only difference is, isn't it? It's always there, no matter Kepler and Galilean. And this is the principle, it's always there, isn't it? Secondary focal point of I secondary focal points of objective lens coincide with the primary focal point of ocular lens. It's always same. It doesn't matter. What is different is in case of Kepler telescope, eyepiece is positive. In case of Galilean telescope, eyepiece is negative, minus lens. So magnification is negative. What do you mean by that? Object is erect, image is inverted. Okay, so image is inverted and real. So not prism are added to upright the final image in terrestrial telescope. So since if we want the image to be upright, then we have to use uh, prisms, or there are other methods too, but let it be. So this is the principle, isn't it? Objective lens secondary focal point is here, and eyepiece primary focal point is here. So both coincide, then parallel light comes, and this is the angle of incidence, and this is the angle of refraction. So angle of refraction is much larger, and it creates what? It creates angular magnification. That's the concept. Or in another way, magnification can directly be calculated by minus f2, what is as eyepiece divided by f1 objective length. Very simple. Okay. So let's come to the another very important topic, that's aperture stop, and then we'll again discuss about entrance pupil and exit pupil. There are a lot of students, even fourth year students, they don't know about the entrance pupil and exit pupil. I don't know why, but There are a lot of people who don't understand about entrance pupil and exit pupil, and they don't understand why it really affects the quality of image. So we always tell, isn't it? Kepler telescope has good image quality, but they don't know. They don't know why. If you ask the student why Kepler telescope have better image, they only tell that exit pupil is outside of the system, and that's why. Yes, why exit pupil is outside of the space? They don't know. Okay, I'll tell you why. First, let's discuss aperture stuff. So physical aperture that limits the light entering to the system from an axial object. That's the definition. So it's a physical aperture. What it does is limits the light entering to the system. Okay, it limits the light entering to the system. It's very important, not exiting from the system. Aperture stop means it limits the light entering to the system. Okay, so objective lens serves as a aperture stop, both Galilean and Kepler telescope. See, let me tell you, let me make it clear. In case of our eye, this is cornea, and this is iris, and this is lens. In case of our eye, cornea, lens, and their pupil. Pupil act as an aperture stop. Okay, pupil controls the light. Pupil actually limits the light entering to the system of our eyes. That's why pupil is actually aperture stop. Okay, so that's what I am talking about. In case of our eye, aperture is of this. Okay, so I will tell you in again in case of I am talking about when I am talking about exit pupil and entrance pupil. So this stops the light, but in case of telescope, we don't have anything, isn't it? We have only, see, this is eye ocular lens, and this is, sorry, this is not ocular objective lens, and this is eyepiece. So objective lens itself acts as a aperture stops for both Galilean and Kepler telescope. It's really important to understand this concept. Okay, so objective lens itself acts as a aperture stop. This is very huge and very important point. I'll make sure you understand this concept. So objective lens serves as a aperture stop in both Galilean and Kepler telescope. Okay, now here we come to entrance pupil and exit pupil. So definition of entrance pupil. Entrance pupil is the image of an aperture stop formed by any lenses in front of the aperture stop in optical system. Okay. At the same time, definition of exit pupil. An exit pupil is a image of an aperture stop formed by lenses following the aperture stop. So let me make it clear. Okay. So this is cornea, and this is our pupil. Okay, and this is the lens. The aperture stop is pupil. So in our eye, the aperture stop, image of a aperture stop, that is image of pupil, made by anything in front of iris, in front of pupil, isn't it? In front of pupil, made by anything in front of pupil. In front of pupil, what optical system lies? Cornea, isn't it? So image of a pupil made by cornea is our entrance pupil in case of eye, isn't it? See, entrance pupil is the image of an aperture stop. In case of our eye, what is aperture stop? That's our pupil, formed by the lenses in front of the aperture stop of an optical system. It doesn't matter if there is thousand other lenses, it doesn't matter, but it should be lenses that is in front of the aperture system, aperture stop. In our case, pupil is the aperture stop, and upper image of a pupil made by the cornea is actually entrance pupil of our eye. So that's why in our eye we say entrance pupil is 13% larger, isn't it? So at the same time, exit pupil, image of a aperture stop made by lenses that are in made by lenses that is where it must be in a lens side, because exit pupil means the after the aperture stop, isn't it? All the lenses, image of a iris, image of a image of a aperture stop made by all the optical system after that aperture stop, which is basically lens in our eyes. That's why it's 3% larger in our human eye. But see, this is the case. In telescope, entrance pupil is an image formed by objective lens of a aperture stop. So, see, I'll tell you one thing. In case of our telescope, in case of telescope, let me be clear. In case of telescope, here is the objective lens. Here is the what eyepiece. In case of telescope, there is no entrance, there is no aperture stop. That's why there is no entrance pupil. The only entrance pupil is objective lens itself. It's very important point. Try to just remember it. We don't have any aperture stop. If we have aperture stop here, then entrance pupil is image made by this objective lens, and exit pupil image made by this eyepiece. But we don't have anything like that, do we? No, we don't have anything in between two lenses. That's why aperture stop and entrance pupil both are same thing. That's very important. You have to understand this concept. And then exit pupil. What is exit pupil? That aperture stop, image of a aperture stop made by eyepiece, because it's behind that. So that's why image of a objective lens made by eyepiece is known as exit pupil in our telescope. I'm again repeating it. Image of a eye image of a objective lens made by eyepiece is known as a exit pupil. In case of telescope, entrance pupil and aperture stop both are same thing, which is objective lens. So that's the definition of entrance and exit pupil in case of telescope. But in case of our eye, I have already told you. In case of our eye, let me draw. Wait, let me draw here. In case of our eye, we have lens and cornea. We have, this is aperture stop, which is pupil. Image of a pupil made by cornea is entrance pupil, which is 13% larger. Image of a uh, pupil made by lens, which is 3% larger, is a exit pupil. This is exit pupil lies here, entrance pupil lies here, because pupil, image of a aperture stop made by anything in front of it, image of a pupil made by any image of a pupil made by lens, so behind it. So that's the way to think entrance pupil and exit pupil. So why we need entrance pupil and exit pupil? Another definition of magnification is entrance pupil divided by exit pupil. We can also calculate by like this. Okay, so exit pupil in case of Galilean telescope. See, now it comes. Why? Now I'll tell you why in case of Galilean telescope we have exit pupil inside of the system. In case of telescope, sorry, Kepler telescope, we have exit pupil outside of the telescope. Okay, see, so this is the aperture stop, isn't it? Because objective lens itself aperture stop and itself entrance pupil too. So aperture stop and entrance pupil too. So image of an objective is lens made by ocular lens. So ocular lens has secondary focal point where? It has secondary focal point here, not here. Okay, because ocular lens is negative. Negative lens has secondary focal point here, primary focal point here. So image of an objective lens made by ocular, which is negative lens, it makes where? It makes definitely in secondary focal point. So secondary focal point lies between objective lens and eyepiece. That's why exit pupil in case of what? In case of Galilean telescope is always inside of the system, because secondary focal point of ocular lens lies inside of the system. See, that's the difference. Now in case of Kepler telescope, definitely this is aperture stop and entrance, both same thing. An image of an aperture stop made by ocular lens. So ocular lens in case of plus lens has, sorry, in case of plus lens has secondary focal point here, which means here, outside of the system. So because exit pupil is outside of the system, we can place exit pupil closer to our eye That's why illumination, retinal illumination increases. That's why quality of image increases. But in case of Galilean telescope, the exit pupil lies inside of the eye. We cannot place exit pupil closer to our eyes, to our iris, as compared to Kepler telescope. That's why image quality, retinal illumination in case of Galilean telescope decreases. It's all the game of exit pupil. You must understand why exit pupil lies inside of the system in Galilean telescope and why exit pupil lies outside of the system in Kepler telescope. It's central important to understand this concept. So, in final, objective lens in case of Galilean is always positive. Kepler definitely positive. The only difference is in case of Galilean telescope negative eyepiece, here positive eyepiece. Since it's negative eyepiece, it makes erect image. Okay, it makes virtual image. So since it's negative lens, it makes exit pupil within tube length, it makes exit pupil outside of the tube lens. Because of negative, it's a fail. uh, Sorry, because of the exit pupil is inside of the system, it has less field of view. Because exit pupil outside of the system, it has greater field of view. Tube length is shorter because of negative lens, and tube length is longer because of positive lens. Shape is straight or maybe bend because if we need prism for to correct the inverted image to again erect image, then sometimes when we use prism, it may be bent. So weight, definitely Kepler telescope has higher weight because of its tube length is longer, isn't it? It's simple. So ideal feature of optical design of telescope: appropriate magnification, wide field of view, minimum aberration, excellent lighting, and higher retinal illumination, lightweight, compactness, loss cost, and focusability. So basically calculation is very simple. For distance, we use best corrected visual acuity and divided by target visual acuity, isn't it? That's it, simple. So it's all things I have already discussed here. So aberration, there is we have to minimize the aberration by using anti-reflection coating and by using other uh, small aperture and all these things. I'm not going to deep down because I'll definitely make one large video for aberration. I think I'll cover aberration in 4 or 5 videos. So let's move further. Light transmission. So we will use anti-reflection coating and just pause the video and read all the things. Retinal illumination, as I have already discussed, because exit pupil lies outside of the system, that's why retinal illumination is far better in case of Kepler telescope. If exit pupil lies inside of the telescope, then and another point, uh, the exit pupil diameter of the objective lens divided by this, which we know it, isn't it? Because the see, I'll show you. Magnification of telescope is what we call entrance pupil divided by exit pupil. Since we know entrance pupil is diameter of objective lens, that's why this formula derived. Many of the students don't know why this formula comes, because this formula comes from here. Actually, magnification is equal to entrance pupil divided by exit pupil. The entrance pupil itself, the diameter of objective lens. That's why we put diameter of objective lens. Don't confuse with this formula, okay? So relative light efficacy is entrance pupil is squared. Retinal illumination, I have already told you why retinal. And one thing there you have to understand: the exit pupil of the telescope is larger than the eye pupil diameter, then image brightness remains same. The only possibility that exit pupil of the telescope is way smaller than the pupil of the diameter, then reduction of brightness. Just pause this video and see. Okay, weight, we know it because Kepler telescope has higher weight, and then Galilean telescope because of the tube length. Okay, so compactness and expense, and we know it compactness and how we make it compact. Just pause the video and watch. So it's simple. So today I'm rushing in the last minute because I think I have to cover this in low vision section. When I start low vision videos, then definitely I'll cover it. I took a lot of things here. This is the best book to start. I have taken few things from this book too. Essentials of Low Vision, and obviously great book and my favorite book of all time, Professor Dr. George Archimedes. Okay, bis dann. Okay, choose. Bye.